Ah, for the good old days. Wasn't that a beautiful Model T? And then again, wasn't that a beautiful Corvette? It all depends on your point of view. One thing is for certain, the old cars were easy to repair. Well, things have changed. Added conveniences and government regulations, anti-skid and airbags, four-wheel drive and four-wheel steering, even environmental temperature control. The method? Electronics, computers, the little black box. The Corporate Training Department of Standard Motor Products presents this video training program as part of our continuing effort to keep you up to date in how to repair today's cars and remain profitable. This Four Seasons Environmental Controls training module gives an update on automatic temperature control for domestic vehicles with self-diagnostics. In order to confidently and profitably repair these systems, the mechanic must have a set of hand tools and basic air conditioning test equipment. Also, he must have a thorough understanding and hands-on experience in automotive air conditioning and heating systems. In addition, he should have a thorough understanding of automotive electronics and automotive electrical control devices. I'm sure you're wondering, what will I learn by watching this program? Well, as you follow along with this video, our intention is to supply you with the basic information needed to profitably repair automatic temperature control systems. We will begin by briefly discussing how an automatic temperature control system works. That is, how the components in the system interact with the computer to automatically control the environment inside the passenger compartment of a modern automobile. We will also discuss the components involved in the three most popular late model systems from Ford, GM, and Chrysler. And lastly, and most important, we will teach you the proper diagnostic procedures to solve problems associated with the systems in use today. Ready to begin? In this vehicle with manual air conditioning, the actual control of the air temperature in the car at any given time is dependent upon the vehicle's operator moving the temperature lever on the dash panel to manually select heat or air conditioning. The speed of the blower motor is also manual. We know that the most automatic function of the entire system takes place in the air conditioning mode. During AC operation, various pressure switches and/or temperature switches connected with the refrigeration cycle turn the air conditioning compressor's clutch on or off to maintain the evaporator core temperature. In an automatic temperature control system, the vehicle's operator merely selects the desired temperature, and electronic components in the system handle the rest of the task. The fully electronic systems now regulate the blower speed, the compressor cycling, and the position of the air doors to control the system at a preset temperature. The heart of the automatic temperature control system is an electronic control assembly. This black box is nothing more than a computer, a very sophisticated computer at that. In most modern systems, it even contains a self-test or self-diagnostic system. It can test both the sensor inputs, the output devices, and its own ability to control the temperature of the vehicle. In some vehicles, it can even detect a malfunction and substitute a fixed value for a failed sensor, all to keep the passenger comfortable. Regardless of whether it is a Ford, Chevrolet, or Chrysler, the electronic control assembly serves the same basic function. The computer takes readings from various sensor inputs, makes decisions, and responds with signal outputs to various control devices. The number of inputs vary by year, make, and model, but the input signals to the computer can consist of a sun load sensor, an in-car temperature sensor, an ambient or outside temperature sensor, an engine temperature sensor, an AC high-side temperature sensor, an AC low-side temperature sensor, and the information set by the vehicle's operator on the dash control panel. The computer uses the information from the sensors to compare to its internal programs, and then responds with outputs to control: the speed of the blower motor, the position of a series of air control doors using either a DC motor or vacuum, including a blend air door, a floor or panel door, defrost door, recirculate, or inside air door, etc. It also controls the air conditioning compressor clutch and the self-diagnostic system itself. Let's take a look at the various components in automatic temperature control systems before we continue. The sun load sensor. Both Ford and GM use sun load sensors in their automatic temperature control systems. The Ford sun load sensor is a photovoltaic diode, or photocell. It produces a voltage signal within the photovoltaic device itself. Voltage output changes when exposed to different amounts of sunlight. The GM sun load sensor, on the other hand, is a thermistor or variable resistor. It does not produce or generate a voltage signal. It is sensitive to the heat of the sun. The greater the amount of sunlight hitting the sun load sensor, the hotter it gets. Therefore, the lower the resistance. The in-vehicle temperature sensor is used by all manufacturers. The in-vehicle temperature sensor is located where it has immediate access to the passenger compartment's inside air. This sensor is a thermistor or a variable resistor. Most of the vehicle manufacturers mount the in-vehicle temperature sensor to a component called an aspirator. In some instances, a small blower motor is used to draw air through the aspirator and across the temperature sensor. In others, a vacuum or a Venturi principle is used in the aspirator or ductwork, again supplying a continuous flow of inside air across the temperature sensor. The next component is an ambient temperature sensor. It is normally located in the engine compartment or in the intake air ductwork. It is also a thermistor, and it is used to measure the outside air temperature. The outside temperature reading compared to the inside temperature reading allows the computer to make a decision on door position and to calculate the rate of heat exchange across the evaporator. Engine temperature is also monitored. When the engine is extremely cold, the computer would prohibit the blower fan from attempting to circulate cold air into the passenger compartment until the engine's temperature comes above a preset level. As you can see from these various control panels, each manufacturer or each model within a manufacturer has their own ideas of what the control panel should contain and how it should be laid out. But basically, they all perform the same function. They allow the vehicle operator to select various modes of operation. For example, defrost, warm air, cool, automatic, bi-level, dash panel, floor, recirculate, inside, outside, etc. Also, this panel will display diagnostics codes when requested. The blower operation can be controlled by the computer automatically or set in override manual control in most systems. The control of the blower motor by the computer assembly can take two basic forms. It can be controlled either directly or indirectly. In most cases, the computer sends a signal to the blower motor controller circuit, which in turn picks a speed for the blower motor. If it were controlled directly, the output current flow to the blower motor would travel through a series of resistors and/or relays. But most late-model automatic temperature control systems use a blower control module or power module. In these circuits, the actual speed of the blower motor is a function of a switching transistor. The switching transistor completes a ground path for the blower motor. The blower speed is controlled by switching the transistor on and off, therefore turning the blower on and off very rapidly. The faster it turns on and off, the higher the blower speed. The slower it turns on and off, the lower the blower speed, similar to the duty cycle in a feedback carburetor. The computer also determines how much air is sent through the heater or evaporator core to provide the desired heating or cooling of the interior of the vehicle. This can be accomplished with a heater water control valve or air mix door. The air mix or blend air door is located in the ductwork and pivots by varying degrees or percentages, blending both the evaporator core air, outside air, inside air, or recirculated air to control the desired temperature. Because of the critical nature of the door position, the blend air door in most ATC systems is controlled by a very small DC motor. This DC motor is hooked up in a feedback network. This feedback loop provides a very accurate control and also supplies a very accurate position signal back to the computer assembly. In addition, various air distribution doors are found in the ductwork to direct the airflow within the passenger compartment. In most cases, these air distribution doors are activated by vacuum signals, but certain vehicles now use DC motors for all AC door movement. The computer also controls the air conditioning compressor clutch. Again, this can take place either directly or indirectly. In the direct method, the computer, in conjunction with the relay, simply turns the compressor on or off. In the indirect method, the computer sends a signal to a power module. The power module switching system turns the air conditioning compressor clutch on or off. The compressor clutch ground circuit is switched with a power transistor or electronic relay. Also, in some systems, your knowledge of the engine control computer will be very important. Many systems tie the engine control sensors, power steering pressure switch or throttle position sensor, into the ATC computer to prohibit clutch engagement under certain circumstances. Remember, the temperature control computer not only controls the ATC output devices in response to its signal inputs, but it can also communicate or exchange information with the engine control module and, in certain vehicles, an intermediary computer called the BCM or Body Control Module. This controls all vehicle computer functions, acting as a traffic controller. That's it. We have covered the basic components of an automatic temperature control system. Now, let's take a look at some actual problems and follow through the diagnostic procedures on each manufacturer. Ready? The first step to a logical approach to troubleshooting is ask the customer the questions necessary to determine exactly what the complaints are. The second step will be to check the car out to verify the complaint. Always run a system performance check before starting to work on the ATC system itself. The majority of ATC performance problems are not with the electronics or the controller, but are basic refrigeration system problems, like no refrigerant, a broken hose, a blown compressor or clutch, etc. With our trusty air conditioning thermometer inserted into an outlet duct, operate the system. Run through the various modes checking airflow, cooling, heating, and air distribution. Once the complaint of poor cooling has been verified, always check the obvious. Verify that the vehicle's cooling system has an adequate level of antifreeze. Connect a gauge set or a charging station and do a refrigerant system performance check while monitoring the pressure gauges for proper ratios. If no refrigeration problems are found during the preliminary investigation, it is time to look at the electronic automatic temperature control (EATC) system itself. Since this system has onboard diagnostic capability, the next step would be to enter the self-diagnostics mode. This Cadillac Seville probably has the most sophisticated onboard diagnostic system ever produced. General Motors installs a comparable system, though the display panel may be different in other vehicles in their model lineup. So why show the most sophisticated system first? Is it the most complicated to use? That's a good question. After you become familiar with working on any of these General Motors systems, you will find them extremely informative. Older General Motors vehicles, including 1985 vehicles with digital fuel injection, had automatic temperature control onboard diagnostics. As each year progressed, more and more trouble codes were added to the system. Now, let's proceed with entering the diagnostic system on this Cadillac. General Motors refers to it as service mode. You should note that the self-test system may be operated with the vehicle off and the ignition key on, or with the air conditioning operating. In fact, you should note that operating the vehicle in the service mode with the engine off can cause quite a drain on the battery over a period of time, and with a low battery, it is possible to receive false diagnostic information. It may even be advisable to attach a battery charger to the battery at a low charge rate if the vehicle is not going to be operated during the self-test mode. To enter self-diagnostics with the ignition key on, push the off and warm buttons on the climate control panel and hold for a few seconds. Remember, this off and warm button selection will trigger diagnostic codes in most all vehicles since 1985. Certain early vehicles may require the off and auto buttons to be pressed. While this system is entering self-diagnostics, the first thing you will see displayed are the trouble codes that have been retained in memory. These codes can be listed as current, those detected during this diagnostic sequence, or history, those detected in the past, still held in memory, but not picked up during this sequence. This may be an indication of an intermittent code or a prior malfunction that has been repaired and the codes were not cleared. The normal sequence after the trouble codes will be to display the word ECM ? The computer is asking us, do we want further information on the ECM system? Since we have an E015 trouble code, the answer would be yes. E015 refers to a coolant temperature sensor. Could this cause a malfunction in the automatic temperature control system? Before we proceed with looking at the ECM, an entire series of systems information is available, so we must decide which system we want to select. By pressing the off button, we go to BCM ? The IPC ? If we continue to press the off button, we will exit self-diagnostics. Once we are back at ECM, we want to answer yes. We want ECM information. Pressing the high button will select this as our desired system. ECM input ? If you press the low button, we can move through all of the ECM possibilities. ECM output, ECM override, ECM snapshot. Remember, if at any time we want to exit the ECM program, to press the off button. Continuing to press the low button, we will come to ECM data. We want to see what the inputs to the ECM are, so press yes, the high button. Now that we are in the ECM data, we can scroll through all of the pertinent data by depressing the high button. As we come to E015, we see a minus 38 degrees. Is this possible? Not very likely, and in fact, whenever you see the negative in front of the number, especially a temperature reading, it is a good signal that there is a problem with that particular sensor or its circuit. The next step would be to go check the particular component for an open or shorted circuit using an ohm meter. To illustrate the point, in this case, the coolant temperature circuit of negative 38 degrees can be rectified instantly by plugging the temperature sensor back in and showing what happens. Continuing to scroll through our program, we have no need for additional information in the ECM input area. Pressing the off button will return to the ECM area. ECM outputs, ECM override, ECM clear codes. Since we have already rectified or isolated the ECM-related component failure in this vehicle, we want to clear trouble codes. So depress the high or yes button. ECM codes clear. ECM snapshot. What is a snapshot? Well, just like a camera, this computer will freeze during the test cycle at any instant in time, hold the information in memory, and display it to you so that you can work within a given program segment. Let's take a snapshot. Press the yes or high button. Once the snapshot is taken, you can scroll through all of the information from that moment in time. Press the off button. Yes, we sure do. Input data? No. The BCM output? No. BCM override? No. BCM snapshot? Yes. B112 snapshot? Definitely. B112 data? Yes. This is what we are really looking for, the data that affects the failure of B112. As we scroll through this data, we see a minus 40 degrees low side TPBD, body data 20. This is telling us that we have a low side pressure, or therefore temperature, of minus 40 degrees. Not very likely. If you look through the refrigeration system on this Cadillac, you will see that there are 4 sensors mounted on the pressure lines, 2 on the high side and 2 on the low side. There is a high side pressure and a low side pressure connected with the refrigeration system to control the clutch cycling. There is also a high side temperature sensor and a low side temperature sensor connected with the onboard diagnostic system. With the temperature sensor removed, it is an easy matter using our ohm meter to make an evaluation on the component or replace it with one known to be good. As you can see, with a malfunction repaired, we have 10-degree low side TP. 10 degrees? Yes, all temperature readings and pressure readings are displayed in centigrade or kilopascals. Press off to exit the BCM area. Now press the low to scroll through the BCM. BCM clear codes? Yes, we have repaired the problem. Let's exit and do an operational check. Well, we have repaired the problems, illustrated how to utilize the onboard diagnostic system, and illustrated how easy, or was that complicated, it will be to repair a late model General Motors electronic automatic temperature control system. If you thought General Motors was complicated, you will probably be disappointed when we illustrate the next onboard diagnostic system. Ford Motor Company began using self-diagnostics in 1984-85 Lincoln products and 85 T-Bird, Cougar, and Mustangs. It is still a good system. The Ford system and the Chrysler system to follow will isolate troubles to a specific area. To repeat, the vast majority of automatic temperature control problems are not in the electronic circuitry. They are in the refrigeration system itself. The first step in entering self-diagnostics on this Sable is to make sure the engine is at an operating temperature. Again, diagnostics can be performed with the vehicle running or with the engine shut off and the key on. Next, while holding the off and floor button in for approximately 2 seconds, press the auto button and watch the digital display panel. Any error codes or trouble codes stored in the computer's memory will be displayed in numerical order. Be prepared to write down any of the stored codes for future reference. Unlike General Motors, this system has very few trouble codes, but they will still supply you with the information necessary to generalize the location of the problem. A code 04 signifies an ambient temperature sensor, and a 05 is a sun load temperature sensor. Ambient sensor? We should be familiar with that on a Ford product. It is that sensor mounted out in front of the radiator, and it has been used on Ford for years. In fact, it still looks the same. Sometimes it was used to prevent the air conditioner from coming on when it was too cold for the refrigeration system to operate properly. Here, it is a computer sensor to help the computer calculate the amount of heat transfer. Let's look at the sun load sensor. It is mounted in the left speaker grill, just ahead of the driver on the left-hand side of the dashboard. Looks kind of like an electric eye. It is really impossible to test. In fact, the 05 signifies that this component has short-circuited internally. It must be replaced. After the component has been replaced and the speaker grill has been reconnected, it is a simple matter to run a performance check on the system. Run the air conditioning system from minimum temperature to maximum temperature. Watch our air conditioning thermometer to make sure that it matches to the dashboard display panel. Pressing the warm button will exit self-diagnostics and clear codes automatically once the malfunctioning component has been repaired. In fact, this system does not really retain codes in memory. As you enter self-diagnostics, the entire system goes through a self-test, activating and checking resistances on each component in the system, and displays trouble codes only while you are in diagnostics mode. Once the ignition key has been turned off and turned back on again, the system will release any trouble codes that were present. Easy? Well, yes, but not quite that easy. The main problems with Ford seem to be the blend air door or the feedback signal between the door motors and the door adjustments and temperature correlation of the computer panel. Normally, the various sensors do not burn open or short. Remember, this air conditioning system is really a computer-controlled manual air conditioning system. Instead of the driver moving the temperature bar back and forth, the computer sets a value and adjusts the doors automatically through the use of an electric motor, takes a reading of the door position, holds it in memory, takes a temperature reading, and moves the door. Let's take a look at the Chrysler ATC system. Chrysler uses two styles of ATC. One is found on rear-wheel drive vehicles and is called SATC, which stands for Semi-Automatic Temperature Control. The semi refers to the fact that the system controls or maintains the driver's preset temperature automatically by heating or cooling the incoming air, but it cannot adjust the blower speeds automatically. The system design allows the control assembly to control the routing of air through the evaporator core and then either through or around the heater core to derive the preset temperature. Airflow is controlled automatically by positioning the blend air door to derive the set temperature. The system still contains the four basic ATC components: an ambient temperature sensor, an in-vehicle temperature sensor, an aspirator or air tube, and a control head assembly. Looking at the operation of the system, the operator of the vehicle sets a preset temperature between 65 and 85 degrees. In moving the temperature control lever, the operator is really moving a variable or sliding resistor. As the lever is moved to the right or warmer, the resistance is increased, and if he moves it to the left or cooler, the resistance is decreasing. The output of this control head is connected to an electronic servo motor. The electronic servo motor uses the basic sensor input readings: the in-car sensor, the ambient sensor, the driver's control panel, and matches these resistance combinations to position the blend air door to the proper position. As the driver moves the control lever to a cooler reading, lowering the resistance at the control head, the servo motor reacts by moving the blend air door to a cooler position or lower resistance. The in-vehicle temperature sensor functioning with its aspirator assembly is nothing more than a thermistor that converts its temperature to an electrical resistance value. A change in this resistance affects the amount of current flow through the servo motor, altering the position of the blend air door. The ambient sensor also works as part of this network in the same manner. Remember, the operator must manually change the blower speed in the system. Now let's take a look at Chrysler's EATC system, Electronic Automatic Temperature Control. It is found on front-wheel drive vehicles like this Chrysler New Yorker or Dodge Dynasty. In this system, a computer totally controls the blower speed, airflow, recirculate or fresh air, hot or cool to maintain the desired set temperature. The computer is an integral component of the dash control panel. This system also contains a self-test or diagnostic circuit in the computer. It will read out fault codes to help troubleshooting. A PVM, Power Vacuum Module, is positioned on the blend air door housing. The PVM powers the compressor clutch and blower motor. It also controls vacuum to the heater water valve and certain vacuum motors. The blend air door is controlled by a DC motor wired into a feedback circuit. As the door is moved, it sends a feedback signal to the computer, telling the memory circuit where it is, for example, 15 degrees or 20 degrees, etc. Let's test this Chrysler New Yorker EATC system and repair any problems found. First, conduct a performance check. Start the engine and let it reach operating temperature. Press the panel button on the AC control. Make sure the display lights. With the display lighted, press the defrost, floor, and bi-level buttons at the same time to enter self-diagnostics mode. Note, as of 1988, this button is labeled Auto. You should see all the elements on the display at this time. This is your clue that you have entered the self-diagnostics mode and the system testing is in progress. The whole test will take about 90 seconds. With a notepad in hand, let's watch for trouble codes. A code 14. No other codes are indicated. Before any repair work is started, press Off. If the system were tested and it found no fault codes, a 75 would read on the control panel. The trouble code 14 indicates a problem with the ambient temperature sensor. So let's continue and remove the sensor and check the component. With the glove box panel removed from the dash panel, it is not a difficult task to unscrew and remove the ambient sensor from the air plenum. With the unit unplugged, measure the resistance of the sensor. It should be 3,000 to 40,000 ohms at between 30 degrees and 120 degrees Fahrenheit. This is a very wide range, but normally the component will open circuit when it malfunctions. We have an open circuit, identifying a failed component. With the component replaced, again, do a performance check of the ATC system. Then recheck the self-diagnostic system and look for fault codes. Note that testing and repair of the in-car sensor is done in a similar manner. You can see that most problems can be corrected with the use of a simple volt-ohm meter and service literature and the self-diagnostics procedures outlined. This concludes working on automatic temperature controls. As you have seen, they are not difficult to troubleshoot and repair utilizing onboard diagnostics. I would like to take this opportunity on behalf of Standard Motor Products and its training department to thank you for purchasing this video, and we hope you will consider us for your future replacement parts needs.